This is section 9.3 part B, the one sample t-test. When the conditions are met, we can test a claim about a population mean mu using a one sample t-test. Here are the details. So when you're using a one sample t-test, choose a simple random sample of size n from a large population with an unknown mean mu to test the hypothesis that mu is equal to mu sub 0. First, you're going to compute the one sample t statistic, and our t value is just going to equal the mean from our sample minus the mean given in the null hypothesis, all over the standard deviation of the sample divided by the square root of the sample size. You're then going to find the p-value by calculating the probability of getting a t statistic this large or larger in the direction specified by the alternative hypothesis in a t distribution with a degrees of freedom of n minus 1. So if the alternative hypothesis is greater than, you're going to find the area to the right. If your alternative hypothesis is less than, you're going to find the area to the left. And if the alternative hypothesis is not equal to, you're going to find the area on both sides. So remember, once you find that p-value, you will have to multiply by 2. Using this test only when the population distribution is normal or the sample size is large, and the population is at least 10 times as large as the sample. So the level of dissolved oxygen in a stream or river is an important indicator of the water's ability to support aquatic life. A researcher measures the dissolved oxygen level at 15 randomly chosen locations along a stream. Here are the results in milligrams per liter. A dissolved oxygen level below 5 milligrams per liter puts aquatic life at risk. Can we conclude that aquatic life in this stream is at risk? Carry out a significance test at the alpha equals 0.05 significance level to help answer this question. So we are going to do this as a 4-step problem. Remember, on a 4-step problem, the first thing you're going to do is you're going to do your state. In your state, you need to tell the significance level, you need to tell the null and alternative hypothesis, and you need to explain what you're trying to solve. So for our state, we want to test a claim about the actual mean dissolved oxygen level mu in this stream at a significance level of alpha equals 0.05. Our hypotheses are that our null hypothesis is that mu equals 5, and our alternative hypothesis is that mu is less than 5. Next, you need to come up with your plan. In your plan, you need to determine what type of test or interval you are going to find, and then you need to check your conditions. So because we do not know the population standard deviation, we are going to start with a one sample t-test. Now next, you're going to check your conditions. So the researcher measured the dissolved oxygen level at 15 randomly chosen locations, so the random part has been met. Next is the normal. Because our sample size is only 15, you are going to have to graph the data and see what happens. So if we make a histogram, we make a box plot, both of those look pretty normal. You can also do a probability plot, and that does look very straight. So this does indicate that the sample is pretty normal. There's no outliers, there's no strong skewness. So we can go ahead and use our normal calculations. And then the last thing you're going to check is the independent claim. And because we can assume there are more than 150 places, because 10 times 15 is 150, that they could have checked the stream. There are infinitely many different places they could have stopped and checked. The independent condition has been met. Next is going to be the do part, where you find all your calculations. Now, they gave us the data but didn't give us the mean and standard deviation. So you can take our list of our data points, you can put them into your list 1, you can do the one variable statistics, and you can find the mean, or your x bar, and your standard deviation, which is your s sub x. In this case, our mean is going to be 4.771, and our standard deviation is going to be 0.9396. So first thing you're going to do is find your test statistic. So we're going to do the sample mean minus the hypothesis, so 4.771 minus 5, all over the sample standard deviation divided by the square root of 15 because our sample size was 15. And this is going to give us a t, or our test statistic, of negative 0.94. Now to find our p-value, you can either look on table B or you can do your calculator and find the exact value. But if our p-value, to find our p-value, we're finding the area to the left of negative 0.94. We're going to start by finding our degrees of freedom. So our degrees of freedom is your sample size minus 1, which in this case will give us 14. Table B shows us area in the upper tail of the distribution. So because of this, we are going to look at a positive 9.4 instead of a negative 9.4, but these are symmetric. So the area above positive 9.4 will be the same as the area below negative 9.4. If we look on the table, we are going to find that 0.94 for degrees of freedom of 14 falls between the values of 0.868 and 1.076. And if you go from those values to the top of the table, you can see the p-values that correspond to that are 0.20 and 0.15. So from this, we need to make our conclusion. So 0.15 is less than or equal to our p-value, which is less than or equal to 20. Since this p-value is greater than our alpha level of 0.05, we fail to reject the null hypothesis. There is not enough evidence to conclude that the mean dissolved oxygen level in the stream is less than 5 milligrams per liter. Again, you could have used your calculator to find a specific p-value, and then you could have said the exact p-value compared to the alpha level, but it would still be failed to reject because it should still fall between 0.15 and 0.20. Given our conclusion in part A, which kind of mistake, a type 1 error or a type 2 error, could have been made? Explain what this mistake would mean in context. So since we decided not to reject the null hypothesis in part 1, we could have made a type 2 error, which is failing to reject the null hypothesis when it's actually false. If we did, then the mean dissolved oxygen level in the stream would actually be less than 5 milligrams per liter, but we did not detect this in our significance test. So basically this would mean that the stream would not have enough dissolved oxygen to support aquatic life when we said that we couldn't reject that it actually would. Because the T distributions are so common, all statistics software packages will do the calculation for you, as in the figure below. The output from a mini tab for a one-sample t-test in the previous example has the results that match our previous example. So this is still our dissolved oxygen level. They are giving you your t value, and it's actually telling you the p-value as well. So our p-value is 0.181, which does match our previous answer, which we said was between 0.15 and 0.20, so 0.18 does fall between those two. So when you need to do a one-sample t-test on a calculator, you can let the calculator carry out the work for you. So our null hypothesis was that mu is equal to 5. Our alternative hypothesis is that mu is less than 5, and we have the data points given to us. You're going to start by entering all of the data points into list 1. From there, you are going to hit test. To run the test, you're going to press stat, go over to test, and you're going to choose test 2, which is a t-test, and you're going to select that you're going to do it from data. We know that our null hypothesis is 5. We're going to select that we want to find less than the mean value because our alternative was less than, and then we're going to tell it to calculate. And then it should give you the correct answer. So let's check our understanding. A college professor suspects that the students at his school are getting less than 8 hours of sleep a night on average. To test his belief, the professor asked a random sample of 28 students, how much sleep did you get last night? Here are the data in hours. Do these data provide convincing evidence in support of the professor's suspicion. Carry out a significance test at the alpha equals 0.05 level to help answer this question. So again, we're going to start with the state. We're going to say what the hypotheses are, we're going to define that parameter, and we are going to give the significance level. So we want to perform a test of the null hypothesis as mu equals 8 hours versus the alternative hypothesis that mu is less than 8 hours, where mu is the actual mean amount of sleep the students at the professor's school get each night. We want to perform the test at an alpha equals 0.05 significance level. Next is our plan. You need to say what type of test or what interval you're going to do, and then you need to check your conditions to make sure you can actually do that test. So, if the conditions are met, we should do a one sample t-test for the probability mean. We're just trying to decide if we can reject or fail to reject that null hypothesis. It did not ask us for an interval, so we're just going to do a t-test, not a t-interval. Now we need to check our conditions. So random, it does tell us there was random students selected. For our normal, they only did a sample of 28, which is less than 30, so we are going to have to graph that data to check to make sure there's no skewness, and or not much skewness, and that there are no outliers. As you can see from this histogram, this is approximately normal, so we can go ahead and do our normal calculations. The last thing you need to do is check that independence, which is the 10% condition. So since we selected without replacement, we need to make sure our sample size is less than 10% of the entire population. Since our sample size was 28, 10 times 28 gives us 280 students, and it's very likely that a university or a college is going to have more than 280 students overall, so that 10% condition has been met. So we have met all of our conditions, and we can actually do our calculations. Now we have our data values. We're going to do the do part of this. You're first going to have to start out by finding the mean and the standard deviation of your sample. So you are going to have to put those into your calculator. You're going to have to do the one variable statistics to find your mean and your standard deviation. From there, you are going to find your test statistic. Remember, your t-value is equal to x bar minus mu sub 0 all over s sub x divided by the square root of n. Or in our case, our sample mean is 6.643 minus the mean from my hypothesis, which is 8 hours, all over the standard deviation of 1.981 divided by the square root of the sample size, which was 28. And that's going to give us a t-value of negative 3.625. From here, we need to calculate that p-value. If we do this using table B, because we're finding the area to the left of negative 3.625, that's not going to be on the table. We are going to have to find the corresponding values of the t-value. Probability of t is greater than 3.625. Now we do need to find our degrees of freedom first. Remember, degrees of freedom is your sample size minus 1, which in this case will be 27. And again, we are going to look at a positive 3.625 instead of a negative 3.625, but this graph is symmetric, so they will be equal areas. So we're going to find on our degrees of freedom line of 27, values of 3.421 and value of 3.690. Our 3.625 does fall between those. If you look at the top of each of those columns, we're going to see that our p-value is going to fall between 0.001 and 0.0005. Now this is only a one-tailed test. We are looking for less than, so we do not have to multiply these answers by 2. So our conclusion can be that since our p-value falls between 0.005 and 0.01, this p-value must be less than 0.05, so we reject the null hypothesis. It appears that students at this university get less than 8 hours of sleep on average each night.